My name is Larry Fink. I'm going to talk to you about the velocity modeling updates for Decision Space EP.4.04, and I'm the product manager. So it's very exciting to actually talk about all the new features that we have for 4.04. So I'm going to start out with a quick value proposition, and essentially, velocity is the bridge between seismic time and well depth. And as long as seismic data is recorded in time and the seismic interpretation is used to map out the reservoirs and such, the velocity model is going to be critical value, critical importance, because it'll move the seismic structures up and down. It moves faults and images laterally. It compresses and shrinks rock volumes. So very critical is to get the velocity model correct. So let's talk about what's the new features for 10ep.4.04, and we actually have 9 new major features and 4 new major enhancements. Okay, so lots and lots of things to go over. So a quick safety moment. We're going to be talking for almost 40 minutes of all these new features. Please put on your seatbelt for this, because it's going to be quite a ride here. Okay, so we didn't do all these features in a month or 2 months that we're putting in this 4.04 release. This actually started 1.5 years ago, and this heat map is sort of showing when we developed the features and when they're ready. And so it's 100%. This is when we had everything completely ready for our 4.04 release, and that's why we're so excited to give this all the new features of 1.5 years worth of development. And again, before we start, I want to just do a little background on velocity modeling, in that velocity modeling, it reads, writes, consumes many different data types to give you the most scientifically valid velocity model representation of the Earth. And in this 4.04 release, what we did is we added a lot of features that allow us new ways to consume these different data types, new ways to analyze them, new ways to QC them, and new ways to construct those into a scientifically valid velocity model. Okay, so without too much ado, let's look at the first feature of our 13, is linear velocity analysis. Now, this is new to Decision Space velocity modeling. It's not new to Depth Team Express. So we have a bunch of Depth Team Express replacement features in this release that we're quite excited about. And the big feature here, linear velocity analysis, it's great for people working in basins where the velocity is a function of depth, or maybe a function of geologic layering due to depth. And when we get these, define these functions, it gives us a more accurate velocity model in between the layers as well. So let me just do a quick cartoon showing what we mean by linear velocity analysis. So if we're looking at, say, like the Gulf of Mexico, this blue is slow water velocity, and the velocity increases. Well, in this case, in the Gulf of Mexico, as you get deeper in the shelf, the velocity, when it increases with depth, it increases with depth as a function of the amount of rock on top of you. Not as a function of the amount of water plus rock on top of you. This is a compaction function, since most of these rocks were deposited in the last I don't know, year or two by the Mississippi, spewing North America all over the Gulf of Mexico. So our velocities are a function strictly of the depth below the mudline. An opposing view, if you're in the North Sea, when you got these big old Cretaceous rocks or something, and your water bottom isn't, doesn't look quite like the Gulf of Mexico. It was actually cut during the Ice Age by a glacial cut of the water bottom. So now our velocities are really more just a function of depth below, say, like sea level or something. It's not this compaction. The velocities are more a function of age. So the trick is, how do we define the best function to define these velocities as you increase with depth? Well, we have a tool called linear velocity analysis, and again, this came from Depth Team Express, but we've improved the Depth Team Express one and added a bunch of new features to the Express one. One of the new features that didn't exist in Express is the ability to define these linear functions strictly based on picks time surfaces associated with depth picks, and we can define a nice linear trend. And these QC curves here, these are showing you the error of how well the wells tie based on your certain starting velocity and the slope of the velocities. So we tend to pick where the minimum error is as our starting velocity and the slope of this line. And this line is our linear velocity function. Now, we can also, instead of just using the picks, we can also use the time depth curves for the analysis, and this is what was done in Depth Team Express, is using the time depth curves to help us define a linear trend function. And we can also, instead of using just a single function, we can get an optimal function for every single well, so each well will actually tie, and in that case we would have a variable velocity, sort of laterally variable, and even our slope could be laterally variable if that's how we choose to define our linear functions. So again, a very powerful way to define linear velocity functions to define the representation of the Earth. The next major feature we had was called cross-validation uncertainty analysis, and we mostly added lots and lots of uncertainty analysis to this release. And this, again, is another Depth Team Express feature replacement. In Depth Team Express, this feature was called leave-out analysis, and it's a very valuable feature where you can quickly generate depth uncertainty maps through this cross-validation workflow. So let me just show you kind of what that looks like in the new release. So we've added this new branch called uncertainty analysis, and the first thing in that branch is a cross-validation leaf. And what you do is you input a velocity model that contains lots of wells and picks and stuff. And what we'll do is we'll actually rebuild the model, a new model for every single well, with and without using the well picks, and what that's going to give us is a mistie of how well the wells tie the model, with the well and without the well. Now, if you get a large mistie without using that well, that means this well has a lot of influence on the velocity model, and we ought to wonder, is that true or is that not true? So let me let you see another picture here to show what I'm meaning here. So my red surface here, we could think of this as our cross-validation velocity model surface. Okay, so for example, right here, this red surface would be the velocity model without using this particular well pick. Now, the question is, should the velocity model dip down and in this case make the velocity a lot faster in order to tie this well pick? And maybe for this well pick, should the velocity model get a lot slower to tie this well pick? What we know is there's an error or an uncertainty by using this pick or not using this pick. What we don't know is where that uncertainty came from. Should the velocity truly get faster here? Or perhaps this pick was faulted out a little bit. Perhaps this pick was eroded off. Maybe there's a facies change in here that we're not accounting for. Maybe there's anisotropy. Maybe the seismic interpreter jumped a leg when the time interpretation of where this pick would be. There could be seismic tuning going on. Lots and lots of reasons of why this particular pick might not tie the velocity model. But all we know is its uncertainty. So what we want to do is we actually grid up these uncertainty values and say we don't know why we have bigger uncertainty around certain wells. We just know there's uncertainty there. And so what we do is we give the drillers our best depth estimated map from our velocity model using all the wells, plus we give them this uncertainty map that shows, okay, in this area here, we have our depth prediction, but we also have this uncertainty error prediction. And this says, oh, you're most likely going to be, 100 feet negative in this area if you're drilling. Over here, you might be 40 feet positive when you're drilling. So it really helps the drillers, and a lot of clients really use this quite a bit from Express, and now we can use this in decision space velocity modeling. Okay, the next new feature, and again, second feature in the uncertainty analysis is what we're calling well pick uncertainty analysis. And this is similar to our leave-out uncertainty analysis, but instead of leaving out wells to look at the differences at each pick, what we're going to do is leave out different entire velocity models. So we're going to look at completely a big set of velocity models and see how different parameters in the velocity models affect the well ties for our reservoir horizons, say. So let's take a peek at what that looks like. And here again, we're in our uncertainty suite here. We go to well pick sensitivity analysis, and what we have here is a chart of misties for all of our wells, but now our columns here are actually different velocity models. So for example, this first velocity model is called constant velocity, and then a velocity function of depth. And I look at all of my misties. If I just look at these columns, I can see this V of picks, the velocity function of the picks, has kind of what looks to be the least amount of mistie error. So maybe if I'm only concerned with how the picks tie, this would be the best velocity model to use. Okay. Now, if I click my statistics button, I can run statistics on all of my input velocity models. And again, my statistics show the same thing that I just said, is that this V of picks model has a median pick error of 0.1 meter here, whereas some of these other models are pretty bad. You know, this model over here is fairly decent. It's a good way to analyze all your different velocity models. Now, this also gives us some QC and analysis on our well picks themselves. So if I look at my statistics based on the wells, if I look at this particular well here, I can see the median error of using this well for all my 10 different velocity models is like 2.5 meters. So pretty good. So that's a pretty stable pick, but this well right here has a much larger error. So the other velocity models for some reason couldn't fit this well. So I might go back and look at this pick and see, oh, is that a valid pick, or is something strange going on there? Okay. The next feature that we added, velocity volume uncertainty analysis. Again, it's very similar to just the well pick uncertainty analysis, where we look at a whole bunch of different velocity models and see how they affect well picks. But here we're looking at how my different velocity models affect the volumetrics. Okay, so this is very similar to the 2D mapping volumetrics workflow, where you give it a top surface and a base surface, and then a contact surface, and the contact can be, you know, either a constant or an actual surface. The difference here between this volumetrics and the 2D mapping volumetrics is what we do is we change these time surfaces. Well, they're domain conversions, so we're going to apply 10 different velocity models to move these time surfaces up and down. You know, we let the computer do it, but we'll essentially get 10 different representations of this green volumetric area, and we're going to show you a histogram of what that looks like. So let me just step back again and just have a quick picture. What might 10 different or 8 different velocity models look like? Well, one velocity model could just be a constant velocity, may not tie the wells quite as good, but it is a valid velocity model that they used to use, you know, back in the 50s or something. I can use a velocity model changing with depth, velocity model making sure it ties the picks, this and that. So there's lots of different velocity models you can use, but in this tool, I'm going to input all these models and see how they affect the volumetrics. In the previous tool, I input these different velocity models to see how they affected the well tie top picks. Okay, so when I input, say, 9 different velocity models, I'll immediately see how those different velocity models change the volumetrics. So I don't ever change my top and base time surfaces, but what I do change is how those are domain converted to depth, and that gives me the different volumetrics. And then it'll also give me the different area, because as I move my surfaces up and down, that would change the area of the reservoir as well. and in the last column here, it shows me the composition of what the base is. Was the base of the reservoir clipped by the contact surface, or was the base of the reservoir clipped by the bottom surface, or some combination thereof, contact plus the base? Okay, and then we can look at the statistics of these velocity model volumetric iterations, and we can see, you know, the min and max and stuff. And the reason the statistics are important here is that you typically don't want to use a velocity model that's giving you the minimum volumetrics, nor do you want to use the velocity model that's giving you the maximum volumetrics. Because the question is, why would you have the velocity models on one or the other extreme? You would think the velocity model would come from more in the middle, and the theory is that the velocity models input are all geologically reasonable velocity models. Okay, so the last sort of thing in the uncertainty analysis thing is talking about P10, P50, P90 analysis. You can't really talk about uncertainty analysis without talking about like a P50 and a P90 and such. Now, in decision space velocity modeling, we do already have sequential Gaussian simulation to generate different velocity modeling surfaces, and if you don't know how to do that, you could contact me or support or somebody, and we could show you how to do that. This method here, again, is another Depth Team Express replacement feature, is an alternative method to sequential Gaussian simulation. It's more of a manual P10, P50, P90 statistical estimation of uncertainty. So how this works is, again, in our well-picked sensitivity analysis, where we've given it, you know, 9 or 10 different velocity models, we can give it our time surface, and what we'll do is dynamically domain convert that time surface, you know, in this case 10 different times. So I'll have 10 different depth maps of this this time surface, and then when I have those 10 different depth maps, I can do basic statistical analysis on that, and again get a minimum maximum, but I can also get a P10, P90, and the median, which is the P50. And so I will create these surfaces, and when I create the surfaces by pushing the OK button, I can see what those surfaces look like in my section view, map view, and cube view. And then again, I could use those for volumetric calculations as well. But one thing I'll point out with these, like my P50 surface here, this doesn't tie the well picks in this case. And the P50, again, it's the statistical P50 of whatever your input surface is domain converted. So if your input velocity models don't tie the picks, your P50 is not going to tie the picks as well. So it's a good statistical analysis QC tool here that we can use. Now, speaking of statistics, the next major feature that we added was what we call multilinear regression uncertainty analysis. And that's kind of a mouthful, and this is a completely new feature to our portfolio and something I wasn't really truly aware of before the last few years. And I have to admit, it sounds a bit crazy, but it does work and has merit in certain fields and in a lot of occasions. And what this solution is you input a whole bunch of different grids. Okay, and those grids, they don't have to be time grids or depth grids or velocity grids. Those grids could be gravity, magnetics, electricity, whatever. You could use XYs and just input a whole bunch of data in and let pure statistics figure out what the depths are. And when I mean what the depths are is the depths of the well picks. So we have this linear fit data. So there's this magic algorithm, which is actually not magic. It's basic linear regression, you know, least squares fitting, you know, some matrix algebra here, and that will give us an equation that will, you know, perhaps accurately predict the depths, which is quite valuable, especially when you have limited seismic coverage in an area. So let's take a peek at what that looks like in our uncertainty suite here. In this example here, I'm giving it 2 time surface grids, a velocity grid, a depth grid, and a gravity grid. And I'm also saying, hey, let's see if the X location, you know, distance from shoreline, say maybe that will help me in my velocity prediction and maybe the Y location. So I'm going to go through and generate, a whole bunch of models, linear regression fit models, and try and tie this BCU pick, my base Cretaceous unconformity pick. And after I've generated all those models, they show up in the spreadsheet here, and I can click through, and so like here I've got model 8 highlighted. So model 8 is just using, just say the first 2 time surfaces, and gives me a linear equation of how using those 2 time surfaces you'd get a best depth surface. And then when I highlight this, it shows me what all the residual values of mistying the well picks would be if I use that equation, sort of that model, to represent my depth estimation. And then this graph here is just a histogram of the misties. Okay, so as I dynamically click through here, all these graphs, update together, and we figure out, okay, what's our best model that best ties my wells. Now, once I've decided on the model to use, so it's a linear equation of a whole bunch of different surface grids or gravity grids or magnetic grids or whatever, then I can go through and do an additional analysis and do sort of a cross-validation analysis to figure out what is going to be my best gridding radius to use to add my misties back in, so the actual surface that I generate from this model equation actually does tie the wells. So I have an equation to get a surface, and then I do some mistie fitting to recalibrate to the wells. And this is where we output our final depth grid based on this purely statistical linear regression analysis. If you don't like the gridding, we use the refinement gridding from our Cosmo algorithm to apply the misties back to the grid. If you want to use a different type of gridding, you can just output these the points as a point set and use grid and contour to do your mistie fitting if you want, and you could still use this equation. So a nice powerful tool there. The next major feature that we have is the ability to build models from time and depth surfaces alone. Now, at the beginning, I showed you the graph of all these types of input data that Velocity uses to build a velocity model. One type of data that we did not use for the velocity calculation before was the depth surface. We could use the depth surface for structural control of the interpolation, but we couldn't use it to actually calculate the velocities. Now we can use depth surfaces to actually calculate the velocities, and this is actually very valuable in the 4D workflow, or in the 4D where you already kind of know the depths and the depths have changed, so you want to figure out what the velocities are based upon the changed depths, or in the horizontal drilling resource play workflow where you have predictions of what the depths are, and you want to then use that to find out what the velocities are. Okay, so how that works is you simply give it some time surfaces and depth surfaces, and boom, you have a velocity model. But that velocity model, the velocities are going to be vertically constant between your input surfaces. This picture doesn't show it, but they can be laterally variable. Now, if you want the velocities to be vertically and laterally variable, what you could do is input like your seismic velocities as a background. So here is maybe some seismic velocities coming in, and then we apply this time and depth surfaces to calibrate this model to. So essentially what this tool would do is it would stretch and compress this background velocity model to get it to tie our just time depth surface velocity model. So it's actually a very powerful tool. It's similar to, if you're familiar with the well tie workflow, where you can stretch and compress a sonic log to tie a check shot or to tie your well picks. So the same type of algorithm that stretches and compresses sonic logs, we use to stretch and compress an input velocity model to get it to exactly tie the depth surfaces. So we treat depth surfaces as well picks in this workflow. So what does that actually look like? Well, in our build layered velocity model tool, we've added the two things to our layer-based velocity modeling: to build from just time depth surfaces or to calibrate to time depth surfaces. And essentially all you do is you input a set of time surfaces and depth surfaces, and that gives you a velocity model. If you want to calibrate one, you actually input your background velocity model, say from seismic velocities, and it will calibrate those to this time depth relationship. So quick and simple, and I'm so glad that we have this feature now. All right, the next big major feature is the ability to use XYZ point sets as velocity model input. And this is a big deal for the horizontal drilling workflow. Okay, so lots of companies have all these XYZ point sets that they've used in their horizontal well correlation. However they do it, from lots of different vendors have products to figure out these XYZ points based upon horizontal drilling data. And we certainly have that too, but now we can use the data from other vendors here. Okay, and so how that actually works is in our standard velocity modeling, we've always had this interwell points toggle, which allowed us to read interwell points from our old GeoShaper formatted horizontal well correlation points. But what we did is we changed this to now this is a pop-up selection where you can either select our internally formatted interwell points, or you can select a point set that came in from another vendor, say, in just an XYZ table. And in fact, you don't even have to have horizontal well correlation. You could just add a bunch of XYZ points and say, hey, I want my velocity model to tie at these locations, and it will make the model tie at those particular locations. And we could confirm that by when we look at our pick details, we toggle on this show interwell points button, and it shows how well the model ties the wells, but then it'll also show how well it ties what we use for these XYZ point sets, or what we used for our standard interwell control points. So again, very powerful for the horizontal resource play. Horizontal. All right, the next big giant new feature is time migration stacking velocity analysis. And this is really a major enhancement to our interval velocity analysis workflow we call the IVA workflow. And this is the solution that allows us to produce, geologically stable, defendable, seismic guided velocity models. It really identifies the facies between the wells. Again, so the seismic is the only data that actually touches the rock in between the wells, and we want to use that. And this actually really enhances our geostatistical workflow by using this seismic data in this method. Much more valid than just straight geostatistical analysis. So let me show you what this workflow actually is, and maybe you get an appreciation for it. So typically what we're given is a velocity cube from the seismic processing shop, whether those are stacking velocities, interval velocities, migration velocities, pre-stack depth migration velocities. So the seismic processing shop believes this is a great velocity model. The problem is it doesn't tie the wells. So what we do is we'll extract interval velocities between our layers of analysis. So we define the top and the base, and we'll extract the interval velocities to a point set. Okay, point set showing up in yellow here. Then we'll take that point set of seismic velocities, decompose that, separate it out, and break it up into a velocity trend, a function, plus the residuals. So I could take my residuals plus the trend, and I'll get back to my original seismic velocities from the processing shop. Okay, but then what I'm going to do is I'm going to take my residuals and I'm going to smooth them. I'm going to get rid of all this chatter from the seismic noise, and just what I'm hopefully left with are these facies changes or geologic anomalies that are sort of not regional geologic anomalies that would show up in the trend. These are local geologic anomalies that we've gotten rid of the noise. So those are really what we're excited about. So then what we do is we add these smoothed out geologic anomalies to our trend of velocities, our regional trend, So regional trend plus the local anomalies, that gives us a nice smooth background set of background velocities that we think is a nice geologically stable and valid velocity model for that particular layer. So how we do that is go through our interval velocity analysis workflow, our IVA workflow. So again, the steps that I just showed you, step 1, we convert the seismic velocities to a point set. Step 2, we create a regional function or a linear regression function to define those velocities. Step 3, we smooth the residuals to get rid of the seismic chatter, the seismic noise. And then step 4, we add those smooth residuals back to our regional trend. And so this column here is what we would use for our velocity model. And again, we have X, Y's, and sometimes it's hard to look at the data in a columnar format unless you're an accountant or some kind of wild engineer. So what we've actually added to is the ability to instantly map any of these columns. So anytime we have a table of data, we've added a mouse button 3 option where you can get an instant map of that. So this table has X, Y's, and a mappable value. So mouse button 3, boom, I instantly have a map, so I can, as a geologist, I can see what the velocity trends look like, okay, from any of the tables. Now, if you're a geologist who likes the computer, you can do the mouse button 3 and grid the column so that you can set some smoothing and some other gridding parameters before you look at that instant map. Okay, so by setting the gridding parameters, those are simply just, maybe the number of cells in the grid, how wide you want to expand the grid, the cell size. Do you want the grid to be oriented along the seismic survey? And probably importantly to most velocity model builders, they like this, limiting the output grid to the input data, because a lot of times when you're extrapolating your velocity data, it goes crazy out on the edges. So what people really like to see is what the velocities look like when they're just interpolated between 2 points, not extrapolated beyond points. So I'll talk about this point again later, but I just wanted to make sure you notice this little button here. Okay, next solution 10 is the zone analysis, and we've just added a bunch of columns to our zone analysis table, and this allows us for better QC and correction of anomalous velocity data. And this same trend, garbage in equals garbage out. We want to do as much QC as we can. Most velocity modeling is actually just QCing the data and identifying correlations between the data, so we can build good, regional and local velocity models. So our zone analysis table, just a quick cartoon of what it shows. So for, say, a particular zone, we've got a bunch of different velocity type of data coming in. We've got velocity from well picks, we've got velocity from sonic logs, velocity from check shots and VSPs, velocities from seismic, velocities from grids, and maybe a linear velocity function. So what velocity do we use? Okay, if we want to cheat or something, we could just say, we'll just use the velocities from the well picks, because that's what we spent the most money on. And that's good as long as your well picks are okay. But the question is, as you get away from the wells, how do you interpolate those velocities, and what velocities do you want to continue to use? So we have this zone analysis table, and again, this picture is kind of intimidating. It's a description of all the columns in the zone analysis table, but it's important to understand this table in that it's showing time data and depth data, well pick data, seismic data. It's showing velocity grids. It's showing data from check shots and VSPs, velocities from velocity models. But once you understand the nomenclature of this table, it makes it very, very powerful. So let's just take a look at what the actual table looks like rather than the picture of the columns of the table. So you define essentially the top and your base of your zone of analysis and associated time and maybe some depth surfaces, define different inputs. And this table, again, it's it can be a bit intimidating. You know, it's one of these things I say it may take a day to learn and a lifetime to master, but it really allows you to analyze all the different inputs to a velocity model, and you can start cross-plotting and doing column math to see the differences within the column. So here I've got the velocities from the picks. This column is the velocities from the check shots. This comes the velocity from an input velocity model, velocities from seismic, velocities from somebody's input grid. Added lots and lots of new columns into here. You know, so much data to analyze, and how do we analyze it is, you know, we could make a quick map of it is a good way. We could actually look at even more of the data when we added this button to show all zones. So instead of looking at one zone at a time, we can look at all the zones at once, and maybe we could squirt these zones out, pushing this button to Excel, and you could do analysis in Excel if you're an Excel person. Or what you could do is you could do basic math operations on your different columns. So instead of looking at the delta depth from your well picks versus your velocity model, you could look at the well picks versus the seismic, or well picks versus the check shots or something. You can dynamically make additional columns to our analysis table through column math options. And if you want to look at different statistics, we've added this special statistics called the zero bias velocity, and that just shows up on the bottom of our statistics dialog. You know, other than the standard, you know, min, max, RMS, kurtosis statistics, the zero bias velocity is a velocity that if you could pick one velocity to use within a layer, what would it be? And that's the zero bias velocity, and that's where the sum of the misties of the picks is going to be 0. So you can compare how does your seismic velocities compare to the zero bias velocity or something. So lots of strong analysis tools there. Now getting into some of the usability and some cross-plotting, you know, you're not really a good scientist if you don't do cross-plots and spreadsheets and stuff. So in the cross-plots, what we did is we added where you hover over points in the cross-plots, it'll actually show you the well from which the data came from, and whatever cross plot you're in. So that's pretty nice to look at the anomalies, and you can see, oh, that's from this particular well. And you know, and then if you highlight things in the cross plot, you know, you can immediately see where those points show up in like a map view or a section view or in the cube view. You know, as long as you have those turned on in the view there. And then again, same things, if you highlight the points in the crossplot, they'll show up in the table from which they came from too, so if you want to do the analysis in the table. And again, all of the cross-plotting, histograms, table tools, they're standard decision space tools. So if you know how to do the decision space crossplot, you know how to use the velocity crossplot because they're the same thing. We just get to the data a little simpler and we just pop in the velocity data into the standard decision space functions or tools. Okay, 12th out of 13. We're heading towards the finish line a little bit. We cleaned up our layer-based velocity modeling dialog in that this used to be a bunch of columns where you'd select things that you may or may not use. Now it's just, we're just showing the velocity parameters. So here I can see I'm using a linear velocity function, and if I click in here, I can see how it's parameterized. So here I could use a constant starting velocity or a grid or horizon for my starting velocities. On this layer, I'm using an interval velocity function, and again, if I click in there, I can see that, oh, I'm using this particular interval velocity, and this is how I would select my different interval velocities for that particular layer. The final set of major updates are our usability updates, and I thought Dilbert had a good idea here. If you've got, you know, a zillion functions, you need to make sure usability is on your list of features for your release. So we've added several usability features, and we have some hidden features that you'll be able to hopefully see in the next release. But let's just take a peek at what some of the usability features are that allow us to get cleaner data and save some time. First thing we did is we are now able to tell the difference in our inputs surfaces, whether they're horizons or grids. Our testers were really complaining about whether, oh, when I look at this, I didn't know if this was a grid or horizon input, so we put these little icons that show us, oh, that's a grid input versus a horizon input. And then we also added this collapsible dynamic help area, which we actually copied this from Grid and Contour. Grid and Contour has excellent usability and excellent help, and so we decided to follow in their footsteps and add. So when I'm on a particular node in the workflow, we have this little help area that kind of says, oh, this is what you're supposed to be doing in here, and here's some of the features within the dialog that you're in, without having to jump into pushing a help button or going in to read anything extra. We also added, when we select well picks for certain analysis, we used to have a drop-down menu to select the well picks, but people complained if I have 1,000 picks, it's very difficult to use, so we just changed that to the search and filter icons there to select our well picks. And then with displaying velocities, now we always could, well, since EP, you could mouse button 3-click and do a velocity overlay on a surface, but the velocity that you were given to display on the overlay was the interval velocity. So what we added in this release is the ability to dynamically convert the interval velocity to average velocity, so you can do an average velocity overlay on any of the surfaces in your cube views. Okay, so that's just the velocity from datum, average the velocity from datum down to the surface that you're looking at. And again, that can show you different trends in what's going on with your structure and everything. If you don't like to just look at the velocity, average velocities dynamically, you can actually now mouse button 3-click on the velocity model and export to, or extract to a horizon, and you can output a static horizon for the velocity view, and then you could look at that in a map view, or send that off to different partners that you're working with. The second to last thing we added was just easier launching of the time depth curve editor. Used to be you'd have to go into the well details if you wanted, from this dialog, if you wanted to edit your time depth curves. Now you can just launch it directly from here. And then saving point sets, we used to always just save them as depth. Now you can save them as time or depth, and that just helps in the displaying in decision space for dynamic domain conversion. You don't have to set a velocity model for dynamic domain conversion. And then with the clipping of live data, so here's a slice of the velocity model covering the reservoir area, and the velocities always show up everywhere. Well, now we have a new mouse button 3 on the velocity model, where you can just display the velocity model, a representative of what the input data was. We can clip the model to the surface, or we can clip it to the live data area. And again, like I was saying earlier, just knowing what data was extrapolated versus what data was interpolated is very important. So if I'm doing a domain conversion here, I like to know that, oh, my velocities were extrapolated there, and that might not be as accurate as if they were interpolated. Okay, column statistics we've talked about, and using standard histograms. So the main thing with the histograms we added is this selector. This used to be a drop-down. Now you can just quickly go through and look for anomalies via a histogram of any of the column data that you're analyzing, like through zone analysis or something. And the final new feature here is we cleaned up our main launching toolbar, whereas before the toolbar used to be a bunch of input, delete, input, a bunch of I/O features, whereas now the toolbar is now centric on functionality of all these new functionalities that we've added to velocity modeling, and all the I/O stuff is now in a little drop-down. Okay, so just a much cleaner view, much more powerful view of the toolbar, and that is it. Only 43 minutes worth of great information. All these new features that we've added are really to give you better estimations of depth between the wells. Okay, that's critical for economics analysis, reserves analysis, well planning, and everything. The usability features, allow you to save time and get cleaner data in for your velocity model, so you get the better data in, better QC, because it's very dangerous. If you have garbage in, you'll get garbage out. So we want to clean out the garbage and get good velocity models. And the final point is we designed all these workflows to combat competitive velocity modeling products, and we think we've got a great release here. So I'd like all of you guys to become expert velocity modelers.